What's up, geometry? Thanks for tuning in for another episode of Math with Mullins. Today we're looking at lesson 10.1, lines and segments that intersect circles. So we'll be able to first identify special segments and lines, be able to draw and identify common tangents, and then use properties of tangents. We got a lot going on this page, so just make sure you have each one of these labeled. The first thing we want to know is a radius. A radius is when your endpoints are the center and any point on the circle. It is labeled here in red for radius. A chord is a segment whose endpoints are in a circle. I'd like to think this is kind of like a messed up diameter. It's not going through the center. Instead, it's a chord almost looking like it's a guitar string. A diameter is a chord that contains the center of the circle. So a diameter is a form of a chord. It's called a diameter though because it goes through the center of a circle. A secant is a line that intersects a circle on 2 points. So now we're getting into not segments but lines. Lines meaning they go on forever and ever. So here's that secant. It looks like a chord, but it's going through that circle. A tangent is a line in the plane of a circle that intersects the circle at exactly one point, the point of tangency. Okay? So it's in a plane, meaning it's not going through the circle, but it's in the same area. The tangent ray AB and the tangent segment AB are also called tangents. So notice that you can start with point A and go through point B to make a ray, or you can just make that entirely a line, okay? Or a segment, sorry. Just go ahead and make sure you have these labeled in your notes. So if you need to, click pause, and when you're ready to go on, click play. So what we're going to do is tell whether the line, ray, or segment is best described as a radius, chord, diameter, secant, or tangent of circle C. The first thing we're going to look at is AC, and AC is right here. It looks like AC is just going through the center, so we're going to say this is the radius, whereas AB goes through each thing, so we're going to say this is diameter. Now we have ray DE. This is a tangent ray. And then segment AE, that one will be called a secant. We didn't see a chord, but if we wanted to use a chord, we could say segment AG could be a chord. The next thing we'll talk about is coplanar circles and common tangents. So in a plane, two circles can intersect in 2 points, 1 point, or no points. Coplanar circles that intersect in 1 point are tangent circles. Coplanar circles that have a common center are called concentric circles. So we see some pictures down here. For the blue section, we have 2 points of intersection, but those are not considered tangent circles because there's not exactly 1 point of intersection. But here in red, we are seeing tangent circles because there's 1 point of intersection. In green, we have no points of intersection for these two greens, but when we see a circle within a circle, they are still containing the common centers. These would be called concentric circles. A line or a segment that is tangent to two coplanar circles is called a common tangent. So this would be an example with the red here. Okay. One other thing we want to mention is you can sometimes have internal or external. So internal tangents intersect that when it joins the center of the two circles. External tangents does not intersect the segment. It just joins the centers of two circles. Okay. This might make not a lot of sense right now, so what we're going to do is practice with some questions here. Tell how many common tangents the circles have and draw them. Use blue to indicate external tangents and red to indicate common internal tangents. So if you don't have a red or a blue marker, that's fine. I'm going to get my red and blues situated here, but one thing we want to look for is just making sure we understand internal versus external, okay? So going for that, just keep in mind, external tangents do not intersect the segment that joins the center of the two circles, but common internal segments do intersect the segment that joins the center of two circles. Okay, so let's go ahead and look at this example with A, B, and C and go ahead and color coordinate. Okay, so let's start with blue. Blue indicates external tangents. So blue could be maybe these, how they're connecting. Those are external. You can also have them on like this side, or if you did them on two other sides, you can do that as well. And then internal tangents. I'm gonna use this hot pink for, there's my coloring. These can connect two circles by maybe doing like a crisscross motion. So here's one, and then here's one. Okay, so this one was my blue, and this one was red. So again, for letter B, external, I'm just seeing two tangents I can use. Tangent 1, tangent 2. I'm trying my best to draw straight lines here. And then one internal one, that's just going right through each one for red. And then letter C, we are seeing two external, but because these are overlapping, there are no internal, so we would just say no internal tangents. Okay, so same thing here. Let's see if you can try this one. Tell how many common tangents the circles have and draw them. State whether the tangents are external tangents or internal. You don't need two colors for this one, but go ahead and pause here. Try these on your own, and when you're ready, go ahead and click play. All right, I'm gonna use my same coloring from before. So my external will be here and here. I'm gonna write E next to these. And then internals can just be kind of like a diagonal 1, 2. So that they're just grazing by each one of those. So I and I. Okay. For this next one, not meant to trick you, there is only one external, but there are no internals because they are overlapping here. And number 5, we can't draw an external or an internal, so no external or internal. Okay. All right, let's jump into some theorems. So theorem 10.1, we're going to start with this one. Tangent line to circle theorem. In a plane, a line is a tangent to a circle if and only if the line is perpendicular to a radius of the circle at its endpoint on the circle. So this would be a good picture to draw on your theorem chart. And theorem 10.2 states about the external tangent congruence theorem. Tangent segments from a common external point are congruent. So if the common point is S, that means SR and ST would be congruent. Again, this would be a good picture to draw. I would even draw some tick marks for SR and ST. Okay? So next up, what we're going to look at is ST tangent to circle P? So the first thing we want to know is T a right angle or not? Okay? So that's kind of the question we're asking us. So what we can do is maybe use the Pythagorean theorem and state is 35 squared plus 12 squared equal to 37 squared. So 35 squared is 1,225, 12 squared is 144, and 37 squared is 1,369. They are equal to one another, so yes, ST is perpendicular to TP. Here's ST, here's TP, so that means it's making a right angle right there. So ST is tangent to circle P. Next up, this one states, in the diagram, point B is a point of tangency. Find the radius of C. So we know that it's a point of tangency, which then means that this angle right here should be a right angle. So we can still use the Pythagorean theorem here. We'll start with 80 squared plus r squared, and then on the outside our hypotenuse is 50 plus r squared, right? 80 squared is 6,400, r squared is just r squared, but then 50 plus r squared, that would be like doing this, 50 plus r times 50 plus r. So if you're not familiar with the FOIL method, you're doing first, outer, inner, last. So 50 times 50 is 2,500, okay? Inner would be 50 times r plus another 50 times r, which would be 100r, and then plus r squared, okay? Now we want to be able to just solve for r. So I can go and maybe start by joining this 2,500 with 6,400. Okay, that'll give me 3,900. And then if you notice this r squared, if I minus r squared, it'll cancel out this other r squared here. So all that's left is 3,900 is equal to 100r. So r is equal to 39, which means the radius is 39 feet. Okay, that one took some extra brain power, I'm sure. All right, next up, RS is tangent to circle C. I'm going to zoom in just a little bit here. And RT is tangent to circle C at T. Find the value of X, okay? Because these are tangent, that means they're also equal. So I can say that RT, 3x plus 4, is equal to RS, 28. If I subtract 4 from both sides, I get 3x is equal to 24. So that means x is equal to 8. All right. Now we're going to kind of put everything together with our last few examples. We got questions 6, 7, and 8. Each one has their own circle. So let's go ahead and look. Number 6, is DE tangent to circle C? One way we want to look at that is DE is at creating that right angle. Okay. We know that my radius is 3, so that means this should also be 3. So then I have this right triangle. If you remember your triples, 3, 4, and then 3 plus 2 is 5. So if I plug that into my Pythagorean theorem, 3 squared plus 4 squared does equal to 5 squared, so I can say yes. Okay. Next up, ST is tangent to circle Q. Find the radius of Q. So this is where we have our right angle. So r squared plus 24 squared is equal to r plus 18 squared. Okay. This is where we get that FOIL method. So r squared is staying the same, 24 squared is 576, and then r plus 18 squared is just r plus 18 times r plus 18. Okay. When you FOIL, that's first, outer, inner, last. So 18 times, or r times r first is r squared, plus r times 18 is 18r, plus another 18r, and then 18 times 18 is 324. Okay, so this side will be r squared plus 36r, I'm going to go ahead and combine those r's, plus 324. Okay, I'm going to go ahead and notice my r squareds can be canceled. And then I'm going to move this 324 with the 576 by subtracting it. So I'm going to get 252 is equal to 36r. Dividing both sides by 36, r is equal to 7. Okay. Our last one, points M and N are points of tangency. Find the values of x. Okay. So when we want to find points of tangency, remember that's where we're looking for these two being equal. So just keep in mind, if I have x squared is equal to 9, a lot of you would just say 3, right? Because the square root of 9 is 3, so x could be 3. But if you really want to dig deep in here, technically, you could have a positive 3 or a negative 3, okay? So that would be your leveling up question, all right? That'll conclude our lesson on 10.1. Thanks so much for tuning in. Hopefully this video helped you. If it did, give it a thumbs up, and we will catch you next time when we look at finding some arc measures. Have a great day.